Okay. Welcome back, everybody, again. We have a number of keynotes and visionary talks scheduled throughout the event, and our afternoon starts with a keynote address and a visionary talk, and then followed by a number of regular sessions. I am pleased to introduce our first our keynote speaker of the afternoon, Mr. Serge Leef. Serge joined DARPA in August of 2018 as a program manager in the Microsystems Technology Office known as MTO. His research interests include computer architecture, simulation, synthesis, semiconductor intellectual property, cyber-physical modeling, distributed systems, secure design flow, and supply chain management. He's also interested in the facilitation of startup ecosystems and business aspects of technology. Serge came to DARPA from Mentor Graphics and a Siemens business, where from 2010 until 2018, he was a vice president of new initiative responsible for identifying and developing technology and business opportunities in systems-oriented markets. Please join me to welcome Serge.
All right. Thank you, and thank you, Mark, for the introduction. I'm pleased to be here, and my talk goes a little bit sideways relative to all the test and product engineering topics that you guys have been discussing so far today. So I joined DARPA about 14 months ago, and this is the list of programs that I'm currently running. Just quickly, SHIELD is a tiny chip that is hardware root of trust that enables unique identity, enrollment, and authentication when attached to chip packaging. ACE is automatic implementation of secure silicon. System synthesis meets security. SCATE is side channel attack simulation. ARCHES is design rule checking, or DRC for security. BioSec is application of human immune system as a model for cybersecurity. And then I have a couple of programs in trusted microelectronics. HI3 is domestic manufacturing. Sahara is structured ASICs, secure structured ASICs. And then I have a program called ODrive, which focuses on simulation and optimization of distributed systems like cars and airplanes. And lastly, I am developing a venture fund for Department of Defense that would focus on dual-use chip designs. But I'm not here to talk about all of those things, but just one of them. And so ACE is what Mark asked me to talk about, and so that's what I will discuss today. So the goal of this program that we're just getting off the ground right now is to automate inclusion of scalable defense mechanisms into chip designs and enable trade-offs of security versus economics. And the point that we're trying to pursue is that security is expensive, and it is not a one thing. So security needs to be scalable and adjustable to the problem that you're trying to solve. So for example, if you put a lawn sign in front of your house that claims affiliation with a security company, that presumably deters a certain type of attacker. But on the other edge, even Fort Knox, some people are contemplating, at least in movies anyway. But the point then is, how can we tailor defense strategies and make their economics work for different applications? And so the idea is that there is not a one-size-fits-all security solution, but rather a series of solutions and scalability, where scalability is important. So we are designing very large chips, and humans actually are not very good in dealing with complexity. And so what happens is we inadvertently create huge attack surface in SoCs and ASICs. And so our strategy with ACE is to essentially attack this problem through the notion of platform-based design to create a vertical or horizontal orientation platforms, which are IP clusters, and actually describe them as generators that can automatically create different types of circuits in a scalable way. But the important part is that platforms in ACE contain something called the security engine. And the security engine gets automatically generated and receives capabilities that would defend against these four attack surfaces that we care about. So the notion that we're trying to pursue here is incorporation of security into next generation chips. And we're using platform-based design techniques for this. And since we're already recognizing that we need to weave security into the design fabric, we're using this as an opportunity to actually make some advances in system synthesis. So system-on-chip design process is complicated. One time I was asked to do a speech at my son's high school to explain what I do. And I came up with this chart on the upper right that describes ultra-simplified version of chip design. Well, those of you who are in this business know that this is really, really ultra-simplified. That it's a lot more complicated. But this is, the process is strikingly complex. And unfortunately, we haven't done, and I still sort of think of myself as being part of the EDA community sometimes, we haven't done a good job in EDA in really making a lot of progress in this area. So about the only thing that we've been able to do is to come up with the technology that would synthesize one block at a time. So generating the entire SoC remains an elusive problem. And so we've been able to essentially do synthesis at the block level. And so when the industry started investigating this problem, we basically came up with this graph where we said, hey, it is possible, perhaps, to create this theoretical design, which is infinitely small and infinitely fast. And that really is our aspirational target at the chip level. But we also found that that was actually impossible. And then the next thinking path here was, if we were to find a superhuman chip designer and give him infinite amount of time, he could probably come up with a solution that was pretty small and pretty fast. So since that also was not economically feasible, that led the industry into logic synthesis territory, where we developed a technology where in one day we could create multiple architectural solutions, and then perhaps one of them will be okay or good enough. And they were all worse than what a human designer could do. But over time, synthesis became better. And this curve, called the banana curve, started approaching the origin more and more. And so today, nobody in their right mind would really think about doing logic design manually without the help of logic synthesis. But that is essentially state of the art. We can do sort of one block at a time and then manually assemble all this stuff. And so the limitations here are that an average chip, and the average chip I'm sort of referring to is 100 million gate SoC. That's what we sort of normally see. And with the current design practices, it costs $20 to $30 million to design an average SoC. It takes 9 to 12 months to do it. It's interesting, when I present this data to startups that are focusing on chips, they say, no, 30 million is way too low. It costs a lot more. And when I talk about this to defense companies, they say, what, are you crazy? 9 to 12 months? It's at least twice that. So bottom line is, it is a complicated process. There are many human-induced errors. And at the end of the day, we end up with unpredictable power and no security. And so the dream in EDA for a long time has been system synthesis. In other words, can we take this Can we somehow describe our system at the high level of abstraction, perhaps above implementation, and then automatically have a tool automatically implement for us the entire SOC, not one block at a time, but the whole thing. And when we were thinking about it back in the late 80s, the thought was, well, what we're really trying to solve here is an optimization problem. We're trying to come up with a design that trades off performance versus size. But now if you start thinking about this problem, you have to consider that that's not really enough. Now you have to add power to this argument. So now if you were to do a system synthesis, you have to say, okay, it's performance versus size versus power. And I assert that the time has come to actually think about it even more broadly. There are now 4 parameters that you have to start thinking about optimizing: performance, size, power, and security. And security is a vague concept, so we need to get our arms around it before we even understand what it means to optimize for security. So what is security? At DARPA, we had to take a step back. So just within DARPA, at least, we would have common understanding of what we're talking about when we say secure silicon. And so we basically defined chip-level security as having 4 components: side channel attacks, supply chain attacks, 4 attack surfaces. Side channel, supply chain, reverse engineering, and malicious hardware. And when you bring these things together, that means you really need to optimize a system like this on at least 7 dimensions. It's actually pretty aggressive thought, since the current state of the art is 2 dimensions. So this brings a lot of challenges that we have to consider. Key challenges are quantification of security. What actually is security? The other challenge is, how do we rapidly estimate attack resistivity? And lastly, how do we optimize in this 7-dimensional space? So when we started thinking about ACE, our challenge was to define security in a way that allows us to make progress. Because you could say, well, security is complex, and it's hard to get your arms around it, so it's hard to know if you've made any progress. So we decided, okay, so let's take a look at what's going on right now. First, in software security, there's a lot of activity. There are a lot of commercial players. The academic research is still going on, but bulk of it in software cybersecurity has already happened. And so we're not going there. There's another part of DARPA called I2O, Information Innovation Office, that has a lot of activity in software security. Then there's another security sort of surface that is worth considering, and that is a hardware-software interface, where software can exploit hardware weaknesses. Again, outside of our scope, because we have a program in microelectronics, microsystems technology office called SITH, which actually focuses on that interface. So what are we focusing on in ACE? In ACE, we're focusing basically on the hardware attack surfaces. And these attack surfaces are side channel. So side channel is adversary's ability to extract secrets from our chip. The next attack surface we consider is reverse engineering. In other words, can an adversary extract some kind of algorithmic knowledge from our design? Another attack surface is supply chain. Can we basically detect counterfeit, cloned, essentially non-genuine parts being represented as genuine? And lastly, it's the malicious hardware. Can an adversary incorporate malicious hardware into our design and release the payload based on some future event or a message? And so the model that we use to think about this is the notion of outer and inner perimeter. So in other words, the way we sort of think about this is if you think about a castle that's surrounded by moats and walls, our assumption is the adversary has the barbarians that swam across the moats. They have scaled the walls, and what we're protecting is an iron cage inside the courtyard. And so that's why for side channel attack surface, our assumption is that the attackers are able to listen to the emissions. In other words, we know about people who build walls and moats, and we basically believe that barbarians have defeated those defenses. So our assumption is, good luck to those people, hope they're successful, but we're focusing on inner defenses. inner perimeter. For reverse engineering, we are assuming that the adversaries have the net list. How they got this net list is irrelevant from our perspective, whether they shaved off silicon layers from actual chip, delayered it, or whether an untrusted employee walked out of their facility with the net list. But we're assuming they have the net list. For supply chain, we are assuming the attackers are able to make perfect clones, not detectable by any known tests. And for malicious hardware, this is actually even more distressing. We are assuming that not only did they make it past the moats and the walls, they are inside the iron cage. We just don't know who they are. And so, so that's essentially the problem statement of what of the problem we're trying to solve. So who are we trying to solve this problem for? So if you look at people who design chips today, they broadly fall into this 4 categories. So first you have huge merchant semiconductor companies like Intel, Broadcom, Qualcomm. For those companies, securing their chips is an existential business problem. In other words, it is essential to their business. That's why these companies have hundreds to thousands of engineers focused on creating custom solutions for their silicon. In other words, for every chip they design, there's a different solution that reflects the economics of that application. Then on the other edge of the spectrum are so-called systems integrators, the people like Fitbit, Ring, the intelligent door locking mechanisms and so on. Those people really don't care about security. They, in fact, if they could spend negative amount of money and energy on security, they would. They principally care about demonstrating the value of their end-to-end solutions, and they invest most of their money in the eye candy for your smartphone. And then there's these 2 groups in the middle, and they are the ones that we really are targeting with our strategy. So first group is the mid-sized semiconductor companies and systems companies. These are operations that recognize security to be an issue, but don't have sufficient resources or sufficient economic motivation to do something about this. And then there are defense contractors. And defense contractors do possess deep pockets of knowledge and expertise, but it is very uneven, and they sort of view this as more of an art than science. So we think that we are targeting those groups in the middle, and if we solve this problem for those groups in the middle, maybe we can tell the likes of Intel, you don't need 3,000 people on this. Maybe you can direct 2,000 of them to next generation architectural work. And maybe we can tell the Fitbit folks that, hey, the security thing doesn't really cost you anything. You get it by default. And so a story that I sort of use occasionally to describe what my goal here is that back in the 40s and 50s, US government decided that fluoride was good for our dental health, but they couldn't get the US population to take fluoride and vitamin in pill form. And ultimately, they mixed it into our drinking water. And so that's sort of my diabolical plan, and I would like to mix security into the standard design flows so that whether you want it or not, you're going to end up with more security than what you have now. So we sort of think about security in layers in this. So this is our canonical system on chip. That has a memory, CPU, and a bunch of peripherals. The vision is that we can provide security capability in layers. So at the most primitive level, we can add a piece of hardware to this that gives you hardware root of trust and maybe ability to store some keys. And so that essentially gives you some level of defense against the supply chain attack vector. Next, you can sort of think about, oh, okay, well, maybe we can add other things to this, like support for provisioning, logic obfuscation and locking. Now we need to weave the security engine in such a way that it actually has to touch the peripherals to be able to activate and deactivate them. And then you can start thinking about putting more and more capability into the security engine. And then ultimately, you get to the point where you start thinking about homomorphic computing. In other words, can we encrypt on-chip communication structures to the point where it is very, very hard to attack at runtime. It turns out homomorphic computing is actually quite expensive in terms of area, size, and performance, so deploying it in its full glory is likely unrealistic. But deploying it within the limits of good taste may actually be plausible. And so the way we define the notion of security engine is that as the threat evolves, we need to be able to upgrade the security policies without changing the hardware. And so, by the way, what I'm showing here has very little to do with the actual thing that we're doing in ACE, but it is sort of a philosophical observation as to how you can think of security in layers. We also, in the context of ACE, we thought about threat analysis and mitigation. So one attack vector we considered is, can third-party IP really be trusted? So, for instance, there is a block of IP that is trusted today, and as long as it's inside the ARM building and Cambridge on Fulton Road. And tomorrow it gets encrypted and sent to some customer on the other side of the world, and the day after, an untrusted employee walks out of that building with RTL. And so the question is, 3 months later, when somebody is incorporating this IP into their design, is that the genuine RTL, or has there been some subtle change that makes it questionable? And so for this purpose, we're investigating the notion of IP watermarking, where we would create watermarks and turn them into electrical circuits that are integrated back into the piece of IP, so that these watermarks can be activated either during simulation or in live silicon, and can yield some kind of data that would tell us something about authenticity of this block. And the important part is it needs to survive transformations. So in other words, these watermarks need to survive logic synthesis, they need to survive place and route. In other words, we don't want the design compiler to eliminate them because just because. Another area that we've looked at is the analysis of threats, and that is if you have a piece of IP that has an island of low activity, that's a potential Trojan that's sitting there in dormant state waiting for a trigger. Or if we have an island that is very hard to activate, that's another possibly suspect Trojan. But this also could be because the designer intended it this way. So this is an area where you have false positives. The other thing that we are investing in is the notion of side channel attack simulation. So today, when people design their SoC, they have an option of putting it into an envelope along with a check for $200,000, and 6 weeks later they get a report with what sort of secrets were broken out of this thing. We would like to actually do this automatically. We would like to be able to take RTL or connectivity database, subject it to simulation, and overnight get answers as to whether this design can be compromised, so that the design team still has an opportunity to modify and fix the vulnerabilities found. And lastly, this is an area that has been subject to a lot of research, is the notion of obfuscation, and that is to combat reverse engineering. We want to be able to modify the logic to insert obfuscation technologies so that an adversary cannot easily determine what the intended function is. So the way we sort of go around towards our goal in ACE is we go through this stages, where stage one is called assisted composition, where we take a number of IP blocks and we essentially automatically integrate them using the ACE phase one tools. And so this essentially stitches together a bunch of blocks that are general purpose computing as well as security blocks, and we generate bus interface logic and device drivers and so on. So if you've been around EDA long enough, you know that this type of technology existed in like 2005. So there's nothing breathtakingly new here, but it's a stepping stone that we have to get through. In the next stage, we do something called automated composition. Now we essentially start with the notion of a platform that has a particular set of generators, and the human essentially makes selections that parameterize or configure this platform. And then now we go through so-called automated composition, And now we end up with a general computing portion of the design as well as the security portion of the design. Again, not really all that dramatic. This is something that people were doing in 2015, but it's important to get through this stage, to get to the stage that we really care about, and that is optimized composition. So what we really want to be able to do is, given a particular platform, we would like to give an engineer ability to tell us how important various aspects of the design are to them, and to give us a grade between 0 and 9 for their importance. So you could say performance is not particularly important to me. Size is really important, as in this example. And you can assign cost function values to security metrics as well. And so what we would then do is we would run this through the optimized composition tool, which will compute billions of possible architectural solutions. And some of those may actually be pretty good relative to the original goals. And then a human would be presented with the candidate architectures and then would be able to make some judgments about their goodness by automatically getting an executable C model and running code on it, or if he likes that, getting RTL and running full-blown simulation and whatever. So the idea here is that performance and size estimation models have been designed in the 80s. Power is a challenge, cannot really be computed without embedded software and physical design. Security cannot be computed because it requires embedded software and data traffic. And so the challenge that we posed to our community was that we need to come up with estimators that are very quick to compute and essentially allow us to drive this cost function, which is performance, size, power, and security, with the understanding that power and security are estimates. They only have to be good enough for us to tell the difference between two possible solutions. They don't have to be good enough in absolute sense because it's too expensive to compute them. And so then we could consider using something like combinatorial optimization, which was well understood back in the 80s. And now we can say, oh, okay, well, so if we're designing lawn sprinkler, for instance, I can say that performance is not that important. Size may be important. Power is really important because I expect this thing to run for 12 years on single battery, and security is a don't care for me. And you can see that for different applications, I would parameterize this in different ways. However, if I were to zero in on security and break this out further, my lawn sprinkler guy could say, you know, actually, I do care about supply chain attacks, because if my sprinkler is really successful, there could be people trying to knock off my main SoC. So I'm going to say 9 for that one. I don't really care about reverse engineering. I don't see this as a nation-state attack worthy, but so 9 becomes the driver for this, and that would mean that our tool will generate probably a puff and a key store and some kind of sensor infrastructure, and would try to trade off the size of the solution against the power and size and performance factors that were specified by the designer. So lastly, the other problem we're trying to solve here is design automation or system synthesis. So if you look at what's going on in early startup investment rounds for chip design companies, in red, I marked early rounds of investment in chip companies in the US. So as you can see, there's very little going on. The venture capital community is freaked out by the fact that it costs $20 million at least to get to first working silicon. And so what they see when they look at normal startups is they see the investment profile that is about $500,000 for seed round, about $3 million for A, $20 million for B. But when they look at a chip company, they see something different. And what they see, they don't like. This does not match the economics of venture capital, so it actually is relatively easy to see why there is no investment going into the chip companies. And so it's because it's $20 million to get the first working silicon. So what we are trying to do with ACE is to drive down this cost. We are trying to encourage real advances in design automation, approaching system synthesis. And we're baking security into this system synthesis process. And so we have twofold goals. And one of the goals is, if we succeed with this, we hope to revitalize venture capital investment in chip designs. So that actually is my presentation. So Mark tells me that I had time for 1 or 2 questions, or maybe not.
So we don't have microphone. If somebody is loud enough, can actually get the question answered. We can have 1 or 2 questions. Anyone?
Great. Thank you for listening. Oh, Armenian art?
Yes. I know you read Russian, but you
Yes.
don't need Armenian, so we'll be practicing this later.
Oh, thank you very much.
Okay, let's come here so that you can get a photo.
Oh, the photo.
Yes. Here you go.
Where's the photographer?
There.
Oh. Thank you.
Okay. Thanks a lot. I appreciate that.
Thank you.
Bye-bye. You want to keep it going?
I will. You can introduce the next speaker while I disconnect here.
Thank you.
Those 2 things go together for the next presenter. Here.
Yes, perfect.
Good luck.
Thanks a lot. You can't come back. Okay, we're moving ahead. As I mentioned this morning, we do have different awards that we'll be exercising or mentioning, referring to during the sessions. Here is one. It's a question. The answer is a little bit later. This is about ITC papers with highest citation. And we had a nice AI system that went through the database and selected. Jay has done the job very carefully. Jay is around somewhere. Now, the question is, which publications, which papers you think have the highest citation in the past 25 years? You have read many ITC papers, I'm sure. You may have the answer. Daniel knows what it is. We're looking for citations more than 222. In fact, we have 5 such papers. We'll be seeing them later after the Visionary talk. And I have a second question as well, another one, that is ITC author-wise, the highest citation. Which ITC authors have the highest citation? That is, they have more than 1,000 citations in the past 25 years. There also we have 5 or 6 authors who have more than 1,000 citations. We'll come back to those later again. Meanwhile, we do have a very exciting talk by John Kibarian. John, as many of you know, and he has been a keynote speaker in the past of ITC, maybe a dozen years back, something like that, 10 years ago. John is the president and the CEO of PDF Solutions. He's co-founder of PDF. He has done that back in 1991. PDF is a public company, as you know, for a long time, since 2000. PDF has been doing yield optimization for all this period. And John himself has done research work in the Carnegie Mellon University at the Semantic Center for Rapid Yield Learning. At CMU, he has developed special algorithms to do diagnosing, process variation, and electrical test data, and achieving maximum yield with that. John, prior to that, did his studies, his bachelor, master's, and PhD at CMU, and I think he comes with a CMU delegation today. John.
Okay. I think I'm going to be needing to stay near the mic in order for this to work. Oh, hey, Dennis, could you grab me my water, too? That's my CMU delegation. Help me out with that. Anyway, so first of all, I want to thank everyone for giving me the opportunity to speak today. Yervant is right. This is my second time giving an invited talk at ITC. I now, it's a really old picture of me, by the way. Anjay joked it was my high school picture. It wasn't really, it was the IPO picture, but I've aged a fair amount then. And I decided I know I aged because Yervant said, oh, you're going to give a visionary talk. So that means that you're old. And he said, you know, it's 50th anniversary, and so we're going to talk about what goes on for the next 50 years. I was a bit overwhelmed with that. I thought, well, I'm 55 now, 50 years, I'll be dead, so it's okay to actually predict the future. I won't be around for people to tell me I've got it wrong. But as Yaron also said, I'm a data junkie. I love data. I always love looking at lots of data. So to start this talk, I started looking at data. This is a chart from Kumi. He did a great paper in 2010 when he was at Stanford on improvements in computing over the last, since ENIAC, actually, since 46. And there are a couple of really interesting facts about it, I think, that are quite interesting. If you look at it, he does charts on just improvements in computing over time, performance per watt per dollar, many different ways of slicing. And we have, as an industry, as Art pointed out, done a marvelous job of improving performance per watt per dollar. Moore's Law, Moore made his announcement in 1964. That's when it slowed down. So like a great marketeer, they talked about improvements in performance, but actually before Moore's announcement, we improved performance doubling every 1.33 years. Since then, it was 1.5 years, and now over 2 years per doubling. So why did it go fast before Moore made his pronouncement? We were moving from mechanical switches to vacuum tubes, to transistors, to integrated circuits. Those were big jumps. Then once we went on to integrated circuits and we lived with shrinking, things simplified down, and we kind of actually, to some extent, went to sleep as an industry. If you really think about it, we lived with lithography giving us benefits, Dennard scaling giving us switching benefits, and we moved on. So, it was something encouraging when I looked at this, because when you go back to pre-Moore's Law, we were quite effective at improving performance quite significantly. So, another little tidbit about this, today really still, with all the improvements, it's very difficult to interact with computers, right? Even the AI functions in your computers are relatively simplistic. Anyone that has Siri knows that you've got to speak properly and with not a raspy voice like mine in order for it to actually understand you. And the second quote is a great one, because this just goes to show you, I was an undergraduate in the early 1980s. I found I really liked semiconductors, and so I thought, well, I'm going to go into semiconductors. I read Moore's paper, and I thought, wow, okay, so it's going to double every couple of years, and feature size is going to go down, and this was the transition from 2 micron to 1 micron. So I did the math, okay, lattice constant for silicon's 5 angstroms. I'm 21 years old. Can I get to 65 on this doubling, or am I going to be 45 years old and out of a job because there's no more left? And I thought it was going to be really close. I thought, wow, it's going to be tight, but I really like this field, so I went into it. At that same time, 84, 85, Feynman did a series of lectures on the fundamentals of computing. And I think that quote's actually quite important. If I had read that quote, I might have thought a little bit differently. I was thinking about, atoms and scale and electrons and holes. And, he started postulating at that time quantum computing, right? And how much more the ceiling is for us beyond where we are today, right? And Art alluded to qubits and the challenges that we all have, that they hold every state at once and they interact with each other, and there's many other interesting phenomena associated with them. The second point I just kind of want to make there, we're often limited by the way the frameworks we use to think about problems. And that time in 1984 or 85, when I was thinking about going into semiconductors, my frameworks was silicon lattice constant. There's only it's 5 angstroms, so there's only so small you can go. And Feynman's framework was so much more fundamental than mine, right? And hence he postulated quantum computing at that time, and now we see the first attacks for it. So, what happens over the next 50 years? And I think everyone in the industry talks about Moore's Law yielding to more than Moore, they call it. And often it's another one of these marketing games, right? Folks start talking about more than Moore when they get off the advanced node roadmap, right? They say, well, we can't keep up on the roadmap anymore. We're going to do more than Moore. So I always have this negative connotation with more than Moore. When I hear more than Moore, I think, okay, you're slowing down. You're getting off advanced silicon. You're moving on to other things. And the reality is it really means a lot more than that. And I want to talk about that a little bit today. But advances will not just depend on geometric scaling, and I've got a chart that will really kind of, I think, highlight that a little bit. But if you just look at Feynman's papers, there's another factor of 1 million. We'll maybe never get all of the performance that he highlighted, but as Art said, there's a factor of 100,000 that is necessary. And a big part of that is, of course, power consumption, as Mike Campbell alluded to this morning. Power we have been improving, power we need to continue improving. Already data centers are a very sizable fraction of the carbon footprint, and if we're going to imagine computing driving tremendous more benefits to society, we're going to need to bring power consumption way down. And so, the question that I ask myself is, does more than more mean the end of improvements in advanced computing performance? Are we kind of over and now it's just bringing computing to everything, like IoT? And, again, another one of these things that economics is a very important driver for our industry. And I think, for us, for silicon and for semiconductors and just overall computing, will not stop because there's too much value. This is a quote I read in a paper in 2013 that McKinsey had put out. So 40% of the world's growth over the last 25, 30 years is attributed to the advances in computing, primarily the advances in Moore's law. And so if you just kind of do that math, as Art pointed out, the world economy is $85 trillion. You can argue the economy grows at about 2% at a worldwide level, a little over 2% in America, higher in India, slower in Europe. So that's about $1.7 trillion a year of growth. 60% of that, or 40% of that, is about $700 billion of incremental growth because people in this room and in other parts of the industry have figured out how to make computing get better. So there's tremendous economic value that's out there. The trick has been, in every transition for our industry, where does the value go? And who captures that value, and how does that value get captured? So, of course, in the mainframe era, right, IBM and others captured most of that value. And the PC era is greatly Intel that captured value. And the mobile phone era, Apple is a prime example of value capture, right? They were not doing chip design before the phone comes out. They get involved in chip design as part of driving innovation in the phone. Today, they generate about $65 billion of operating income or gross margin income off the phone itself. And it's actually a better story than that, because if you go and look at their financial reports, more and more of their revenue is services on top of the billion phones that are out there in the world. Now about $40 billion a year of incremental services, high margin services revenue, selling you your videos and your music as well as any content. So, I think one critical thing we've seen recently is all of the major cloud providers are now in the chip business, right, or in chip design, Amazon, Google, et cetera. If you look at some of the biggest efforts in quantum computing, they, besides conventional compute companies, they also exist at the likes of Google and Microsoft and others. So the future drivers of our industry may not be the existing drivers of the industry. In fact, likely will not be the existing drivers of our industry, and probably many of you, we won't be working for the companies we work for today. So I want to kind of bring that into a little bit closer and go over some key points that we think are driving the next 10 years, before we look out to quantum and other factors that we think are changing the nature of our business and what's going to be required for test. So, of course, the first thing is 3D process technologies. That trillion transistor chip is primarily a vertical NAND device, right, where we scale really the geometry of the device and put a stack of 128 transistors high. The picture I show here is a FinFET technologies. But we've moved to 3D, which means we now deal with invisible defects and primarily a lot of electrically related or weak leakage paths and soft open paths that drive tremendous amount and will drive over the next 10 years a tremendous amount of the problems in silicon. The middle chart is a little bit hard for you to see, but I think it's super, super important. So the blue line is the subthreshold slope versus gate length for a 65 nanometer technology. Why subthreshold slope? Because that basically tells you how strong the transistor effect is. How many millivolts of voltage do I have to put on the gate to get a decade swing in current, right? At the 65 nanometer generation was over 100 millivolts per decade. At the 28 nanometer generation, because of high K, we dropped down into the 90s. By the first generation FinFET, we were in the mid-60s. The fundamental limit, based on Boltzmann constant, is 60, 62, something like that. Those little dots on the left are gate-all-around. So what does gate-all-around do, right? The next big thing after FinFET. It lets you drop gate length. It doesn't improve the fundamental characteristics of a transistor. What that means is we're getting towards the end of supply voltage scaling, right? We are getting to the end for silicon of performance improving when we shrink the device. We will effectively be able to shrink the device and fit more transistors on a piece of silicon, but we are not going to see, just for that alone, any incremental benefit whatsoever. It will be very, very marginal. And I think that's really super important. You know, this is a big change in our industry. It's why you're seeing compute shift from, you know, CPUs to GPUs and other architectures, because you need to use architecture as one of the levers to gain incremental performance. That subthreshold slope improvement was what let you drop supply voltage, is what let you got more performance per watt on a single threaded element. There's a lot more electrical scaling that's going on. In other words, introduction of PCM, MRAM, and other new memory elements that you as test experts will have to deal with over these next 10 years. And it's super important to get incremental improvements in compute. And then finally, as people have talked about, we've moved on to a 2.5D to 3D world. And that again means, that's a picture scrunched down of the A10 chip. But if you just look at what's in the package these days, it's quite complex. For everyone that's got a phone, right, you have more than one system in package in your phone. Your modem is a system in package, your apps processor is a system in package, your cameras are effectively systems in package, and your infrared sensor, if you have one of those, is a very complex system in package. This means the price on these things have come way down, right? It's made for great innovation, but it also makes for a lot of challenges that affect you as test professionals and the industry overall. So a couple of those challenges: very complex and long supply chains. You know, that 7 nanometer process is an 80 mask layer process typically. So at 80 mask layer, even at a day and a half per mask layer, is 120 days just from starting a wafer to getting it out. It goes then into a bump facility, and then it's going to eventually go into a package facility. So people today now have 160, 180-day cycle time from wafer start to actual final burn-in tested part. And this is a growing problem for us. It's also a very complex supply chain. More and more customers are buying known good die from their competitors and putting those together in an overall system, or overall system in package. So the multi-chip components often being fabricated, the elements that are in there are being fabricated from many different sources. The previous speaker from DARPA talked a little bit about this, but trust and that supply chain becomes super important, and visibility of the materials is very important. And the last thing is diverse set of trade-offs, right? And he pointed this out in the security. It's also there in quality metrics as well, where folks want to dial in the amount of quality and security they're willing to live with for a system. And as a result, the chip companies are, all of you are becoming system companies, and system companies are becoming chip companies, and even cloud providers are becoming chip companies these days. So our industry is now getting to one where virtually anyone still in the business is a system company. So some of the longer range problems that we think this is going to, people in this room and others need to start addressing. Very high complexity in the system. So today, if you test at wafer sort a 7 nanometer chip, it's going to have a certain level of performance. You're going to put that probably in a very complex package. When you put that in the package, you will thin that silicon. The transistor performance was achieved with strain engineering. Strain engineering gets worked out as you thin that silicon, you release strain. So the behavior of that silicon, that as a wafer at wafer sort versus thinned and put into a package, is totally different. When you put it in that package, how do you know how it's still behaving? What is the transistor actually still doing? When the chip itself doesn't work, now that it's in the package, does it not work because the strain engineering worked out and now there's not as much mobility as there was in the past? This complexity is going to also mean that we as an industry need to work more closely together. This has been something that the industry has talked about for years and found to be very difficult to do. But to get at the overall performance of the system, which is now a package of many elements, we need to understand the interaction of those systems, and no single entity actually controls that manufacturing flow. A lot of the performance benefits are going to come from non-von Neumann compute. I think for many of you might have seen Google announce that they had a 50-something qubit quantum device, and that it could solve problems that would previously take, I think, 10,000 years or something like that. IBM immediately came back with an analysis that said, no, actually, not that substantial. And one of the problems with all of these more advanced things like quantum computing is if the system is set up to solve a problem that you don't really know the answer for, how do you test to know it's actually right? And this is going to be a growing problem for, as computing gets effectively going beyond human intelligence and human understanding. You know, someone said to me once, if you think you understand quantum computing, you don't really actually understand it. You know, you don't even begin to understand it. I think that's very true. Just understanding the way that these systems work is very difficult. How you test one of those systems and verify that it's right is going to become an increasingly challenging problem as we move from a classic von Neumann computer to quantum or neuromorphic or analog computing or any of these more ways that we're going to continue to stay on Kumi's curve there. Varying data sets is going to be a big deal, right? So we as an industry verified hardware for a long time. The EDA industry, Art spoke earlier, right? Synopsys' big push has been into software verification and how do you know the software is right that you're going to go put on that embedded system. When you have systems that train with data, how do you know the data is right? Right? I mean, I have a teenage kid now, and so what data I expose that kid to is a big deal. It's my training set, right? And so, you know, YouTube is a very scary thing for me. There's many data sources that come into that kid's brain that train that, you know, that system that I would like to control in some ways. Training sets, training data, the purity of training data, corruption of training data is going to be a big deal. How do you actually know? Because the system now is not just a piece of hardware, it's not just a piece of software, but it's the hardware, the software, and the data that is effectively the knowledge that's derived from that data. And over time, that's going to be a bigger and bigger issue I think people in this community are going to address. Long-term operation in stressful environments, another factor. I can't wait for autonomous driving. I'm not a big fan of long driving in my car, but you know, I also have tested the systems that are out there and not confident enough with any of them to work, and I don't know that the reliability is there, or the security for that matter. And this is going to be super important on a going forward basis for our industry as well. And that's my last point, the security points. So I think the presenter from DARPA gave a little bit of a talk about the future. You know, we think, you know, Industry 4.0, other parts of the world are actually giving us a good start. This is a little one of my soapbox talks. Again, when I got in this industry in the 1980s, we led the world on analytical methods, right? So Taguchi's methods came from the semiconductor industry, Six Sigma from Motorola, and many in the industry. And now, you know, the ad served on your phone, there's more sophisticated analytics that goes into that ad than most of the algorithms for long-range control inside fabs. There's lots of, you know, sophisticated software on processing tools like etchers and for sure on EUV systems, but by and large, the control loops are very simplistic when you look across the flow. And actually, you know, if you just look at, you know, your world, all the ways that we drive quality at test, you know, I'm always amazed that we do geometric pat separate from doing dynamic pat, right? These are all siloized ways of looking at how healthy is this piece of silicon. Other industries have started adopting 4.0. And what does 4.0 say? 4.0 says that we can use compute and we can take the human out of that loop and have a learning cycle at the algorithmic level. And there are a couple of really important elements to this, not in the order that are presented here. The first most important one is the semantic model or the digital twin. What is your representation of your production process, from producing the chip to testing it to eventually that chip's behavior in the field? The second element is sensors, data you collect, right? So fabs now collect a wealth of data. I think Mike Campbell talked about 2 terabytes of data for chips a day. There's also 2 terabytes of data being collected in the fab every day, too, actually. And those data sets need to come together and be aligned. And actually, as the DARPA speaker spoke about, Serge spoke about, there's a tremendous amount of space inside chips, and instrumenting the chip itself to know something about the chip is also something we're increasingly seeing people do. So there's PVT sensors, there's sensors for inspection and metrology, and there are other sensors that are being developed and put out there. Ultimately, taking the human out of the loop is becoming an important element, A, partly due to bad actors, and B, also just because of the speed that we need to operate at. And direct connection to the tools is really important. So now if you go back to the, my last bullet here is connectivity, right? If you go back to think about the chart I showed on the complexity of the supply chain, right? In the end, the company that's making that chip for their system knows what they want in terms of trade-offs on security, on quality, on performance. Yet that is often done at a series of suppliers, whether it's their foundry supplier, their test supplier, their assembly supplier, or other silicon components. The direct connectivity to the tools, even tools that are not inside your four walls, more and more becomes an important element of the whole operation. So, in summary, the economic value of semiconductors is too big and too valuable for the world to just end anytime soon. We will continue to find a way, I believe, to stay on Kumi's law, even as what was Moore's law slows and eventually ends. There will be significant disruption as part of that. I think the biggest disruption will be business models that allow the connection between the end markets that drive the need for advanced silicon and the folks that need to make the R&D investments. I think if you look at, particularly in the US, one of the challenges that we have is the folks that are generating benefit are the folks that are selling you data, right? Whether it's Facebook or Twitter or Amazon. And the folks that are funding the fundamental learning in silicon are the folks like the foundries and the IDMs and the equipment suppliers. And there's a big disconnect there that ultimately is going to have to get resolved. Obviously, people in this room will make a lot of this happen. I think particularly when we think about what is a good system and what is a bad system, it comes down to you folks. And finally, of course, part of this is going to be tying together the data across the supply chain, as challenging as that's been for our industry over the last 20 years. And with that, I'd like to say again, thank you very much, and end my talk.
Thanks a lot. I appreciate it. Excellent talk.
Thank you.
This is for you.
Thank you.
I think you can read it.
Yes.
Okay.
Otherwise, one is in my house.
Exactly. You have someone. Once you do your ABC courses. Okay.
Okay, thank you.
Thanks a lot. Thanks a lot, John. That was very good. I like the way we link between the different keynotes and visionary talks. John, what you did was very, very interesting. Also, I'm sure Leon tomorrow will be talking about the quantum computing and will connect what you said to the quantum computing part that he will cover during his keynote in the afternoon. Now, coming back to the questions that I asked a bit earlier, as you may see that, yes, this was John's title. So we spoke about the highest citation papers, the papers that had more than 220 citations. So the research of the data shows that we have 5 papers in this category, and the 5 papers are listed here. If we have the authors with us, we'll be thanking them for doing this great job, and we'll be handing their corresponding awards later on. The first one is on embedded deterministic test by Janusz and company. The second one is on embedded core test, Eric Yan, Sujit Day, and myself. Then we have one on IR drop from the TI team, Jashri, Ken, and company. We have one on Optimizer with a team from IBM and Bernd Kuhnemann among them, and Bernd is with us here as well. Congratulations. The last one is on 3D testing, chips with 3D packaging. That also goes to Eric Yan and myself. So these are the top 5 papers that we have, over 220 citations. It's nice to see over many years, it's over 25 years. My second question, again, is for a period of over 25 years, again, that Jay has done the study for. And here we have the highest citation of authors. The previous one was the papers. The authors that have more than 1,000 citations with their ITC papers. The first author is Eric Jan Marinissen, over 1,000 citations. Janusz Rajski, Ed McCloskey, unfortunately not with us anymore, myself, Nur Tuba, and Ken Butler. Okay, so the top 6 authors that we have. I have more questions for you tomorrow, and in each plenary session, we'll be addressing 2 different things, just to remember our authors, to thank them, and also we'll address the exhibitors and the volunteers as well as we move forward. Now, as you know, we promised this morning that we'll do the Global Test Forum together. So we'll be going to the atrium, where we have all the conferences that relate to tests from all over the world being present, with their delegates being there to show you about what they have done and what they will be doing. This blue triangle is where the atrium is. So we'll be seeing you there. Later this evening at 6:30, we do have the ITC Celebration. The ITC Celebration will be the party where we'll be doing the entertainment together, and we'll be celebrating the 50 years of ITC with the sponsorship of Synopsys as patron for that event. There was some request to do some group photos of different eras and so on. We'll try to do that as well. Grady is here, he's trying to organize it. Again, thanks a lot. Don't forget to upload your nice pictures on the mobile app, and don't forget to fill the yellow form. Thanks a lot.